Hi everyone, welcome to another episode of YinsPy. In this episode, we're going to be talking about a high-level overview of the neural network family. In particular, we're going to be talking about neural network, convolutional neural network, recurrent neural network, and how these architectures can be designed into Regressor as well as Classifier. Without further ado, let's get started. Previous episodes, we talked about the feed-forward architecture. To start a neural network architecture, feed-forward is going to be the first step that we do. First layer, we're sending X. These are the covariates, the variables in our dataset. And we're going to process a linear transformation first and a nonlinear transformation, which we call the activation function. The linear transformation has a bias term B and the weights W. And this follows the same procedure as a linear regression. The output of the linear transformation, we're going to throw that into an activation function. And there are so many different types of activation function. There's ReLU, which is short for rectified linear unit. There's sigmoid, there's softmax, tanh, etc. This architecture form a belief. It tells us what's an educated guess for your Y. Is that going to be perfect guess? Of course not. Chances are we're going to make mistakes, but that's okay. There's this thing called a loss function, which is defined here. Your educated guess, y hat, can be compared with the real value y, and you can take a look at the summation of all these errors, of which we call the loss function. This loss function tells us what is our mistake. Based on this mistake, we can update our belief of this w and this b, which are our parameters. How do we do that? We take gradients, which is the partial derivative of loss function with respect to the activation function first. We'll give it a name. Let's call it triangle. And then we take partial derivative of triangle with respect to your weights W and also with respect to your bias term B. These two terms tell us exactly how we should update our parameters weights and bias. And this gives us a backward procedure to transform what we have learned from our mistake loss function into our W and B. And this forward-backward cycle forms one epoch. And in the end, we form some sort of educated guesses. Now, as you can imagine, the more number of epochs that you train your machine on, the less the errors of your educated guess will make. So this is a neural network. What about convolutional neural network? In convolutional neural network, we are assuming that the data set is in a grid structure. Essentially, the data sets are images. So let's take a look at the definition. Convolutional operation is essentially a summation of all of the items from element-wise matrix multiplication. Let's say we have two matrices. A is 3 by 3, B is also 3 by 3. We do the following. 5 times 1, which is here. 2 times 1, which is here. 8 times 1, which is here. The second column of matrix B are all zeros, so we omit those values. And then the last column, 1 times negative 1, 6 times negative 1, 2 times negative 1, and those results are here. And we sum them up together, and the final value is 6. Now, as you can see, this 6 is a transformation of the information that we have in this original matrix A. And this matrix B, in practice, we call it a filter. It is called a filter because it takes information from the first column and the last column and omit everything in the middle. In general, if your matrix A is A by B and your matrix B is C by C, then the new matrix after this operation will be A minus C plus 1 by A minus C plus 1. In practice, this filter is going to be much smaller than the actual picture. So let's take a look at the following example. Let's say you have 561, 246, 872, and your filter is 1010. Now, exactly how this thing works is you have to start this filter from row 1, column 1 of your picture, which is 5624. And then you do your convolution operation. You have 5 times 1, which is here, 2 times 1, which is here. and you're done. And then you shift this filter from row 1, column 1 to row 1, column 2, which is here. So this matrix will be 6, 1, 4, 6. So this will be 6 times 1, which is here, 4 times 1, which is here, and we sum them together. Now we're done with the first row. We move on to the second row of your original picture. So we start from row 2, column 1, which is 2, 4, 8, 7. Now this will be 2 times 1, which is here, 8 times 1, which is here. And you do the same thing with the last one. And this gives you a new matrix, which is 7, 10, 10, 11. So we've shrunk the dimension from the original picture 3 by 3 down to 2 by 2. This whole process is called convolutional operation. Instead of throwing in the neural network architecture, your original pictures, we're now throwing in the newly constructed features as our input layer. And this is what we call a convolutional neural network. On top of that, your dataset could be sequential. Convolutional neural network is probably not going to be helpful for that. Exactly how do we do that? We move on to recurrent neural network. It is a sequential model in the sense that in your covariate matrix, there's a timestamp. So it looks something like that. You have x. The time matters. You have x1 to x2 all the way to xt. And that's essentially how information transforms throughout time. And this is the architecture that we're using. Information flowing from the left-hand side. We now want to construct a feed-forward architecture. So we have our weight and our bias term, and along with x, we can form some sort of educated guess y. And all of these steps are done using the information at timestamp 1. And we move on to 2 and 3 and so on all the way to t. This way, information can transform from beginning all the way to the end, and along the way, we form a series of beliefs about y. Now, of course, as you can imagine, our educated guess y hat is probably not going to be perfect. Chances are we're going to make mistakes. But not to worry. We have this thing called a loss function, which we're going to take gradients of. Just like the loss function in neural network. The loss function in recurrent neural network looks the same, but it carries a timestamp t. Now this is important because not only do we calculate the loss of each time t, we also need to sum all of the loss from t equals to 1 all the way to big T. And we call this overall loss calligraphic L. And this calligraphic L is going to be the term that we use to take partial derivative of. And we do the same procedure. We take partial derivative of calligraphic L with respect to A first. We give that a name, let's say triangle. And then we take gradients of this triangle with respect to each of our parameters, weights W and bias term B. So now we can update our belief from right to left, and hence this is a backward propagation procedure. So from our loss function calligraphic L, we know what is the gradients, which is defined here, and we know exactly how we can update our weights W and our bias term B. And from right all the way to left, each timestamp t, we update our parameters. And that's how we carried out back propagation through time. So there you go. This wraps up convolutional neural network and recurrent neural network. And both of them are based on forward propagation as well as back propagation. One last thing I want to mention is a regressor versus classifier. The difference of regressor and classifier are dependent on the number of nodes in the last layer of the network architecture. For regressor, the last layer has only one neuron. Essentially, what the architecture is saying is in the end of the architecture, we're trying to guess one value, and that one value is a continuous value. Conversely speaking, in the end of the last layer, we can have more than one neuron. And let's say we have k neurons. And this is going to give us a k-class classifier. Exactly what that looks like is in this last layer, we produce an educated guess of y hat on the first node and second node all the way to k node. And then we will check which of these values is the maximum. And the value that is maximum tells us exactly which class this observation falls in. Let's say I've done my math, and it turned out that y hat 1 has the maximum value out of all k neurons. Then this observation is going to be in class 1. And same with class 2, class 3, all the way to class k. And that's how we build a classifier instead of a regressor. So there you go. I hope you liked today's episode. Hopefully, this summary clarifies a lot of the things in the neural network family for you. Thank you for listening. If you want to support the channel, give it a like and click that subscribe button, and I'll see you in the next episode.